Hello, deep learners. My name is Mohammed Danso, one of the TAs for IDLs for 2023 semester. In this recitation, we use block process, another layer of abstraction that will help you in your understanding when reading papers and in implementing your models. As we've learned in class, a single neuron takes some set of inputs, generates a corresponding output, and has a set of associated parameters that can be updated. We then leverage vectorized arithmetic to characterize an entire layer of neurons to form networks with multiple outputs. Just like individual neurons, layers take a set of inputs, generate corresponding outputs, and are described by a set of learnable parameters. A single layer can constitute the entire model, but as we've learned in class, to model a target function, we need a model with the right width and depth. In case of depth, it means that we stack more layers of neurons to increase the capacity of our model. In general, we will tackle most tasks with models made up of multiple layers. While it may seem that neurons, layers, and models provide us enough abstractions to do our work in deep learning, it is often convenient to speak about components that are in between a layer and a model. For example, popular model architectures like InceptionNet, ResNet, etc. have hundreds of layers, and these contain repeating patterns of groups of layers. Implementing such networks layer by layer can be tedious. Thus, we introduce the concept of blocks. A block could describe a single layer, a component consisting of multiple layers, or the entire model itself. From a software standpoint, a block is a class. Any subclass of block must define a forward method that transforms its input into output and must store any necessary parameters. Note that some blocks do not require any parameters at all. A block must have a backward method as well for the computation of gradients, but we don't need to worry about this because of the magic of the AutoGrad package. A block can be seen as an independent entity that takes in an input and provides an output. Usually, many blocks are chained together to build an entire model or to form a bigger block. In the ideal course, you will encounter examples of these in your homework assignments. In homework 2, you will implement state-of-the-art models such as ResNet, ConvNet, EfficientNet, etc., which architecture contain repeating patterns of specific blocks. Homework 3, you will make use of LSTM blocks, probably chaining several of them together to form your models. Finally, in homework 4, language modeling, you will meet the popular and mighty transformer, which is a block that is used in many state-of-the-art models for tasks in speech, text, vision, etc. But a transformer is also made up of sub-blocks called attention. Let's introduce some examples below. Residual block. The image below depicts how a residual block looks like. It has a stack of layers as a traditional neural networks, and additionally has a skip connection. We'll discuss the intuition behind this shortly. The popular ResNet architecture uses multiple repetitions of this block stuff. Now let's discuss the reason for skip connections. We know neural networks are universal function approximators, and that the appropriate width and depth is required to achieve desirable results. But in research, it was later observed that adding more layers does not necessarily result in an improvement in the capacity of the model to learn an underlying function. This is due to some problems like vanishing gradients and the cause of dimensionality. For example, a sufficiently deep network may not be able to learn simple functions like an identity function, which is clearly undesirable. Also, if we train a model and keep increasing the number of layers, we will see that the accuracy will stop improving at one point and eventually go down. So it might seem that the shallower networks are learning better than the deeper ones, and this is quite counterintuitive. But this is what is seen in practice and is popularly known as the degradation problem. So why not skip these extra layers in deep networks and at least match the accuracy of the shallow subnetworks, but at the same time allow us to train very deep networks that can learn complex problems. The picture above is another example of a block. As it can be seen, it has 3 layers. It applies depthwise convolution to its input, followed by normalization, a normal convolution, and activation, and finally another convolution before the result is added to an identity mapping of the input. This block is a key component of the convex architecture.
Now that we have an idea about what blocks are, let's take some steps to understanding how exactly CNN blocks would be coded, and how exactly you proceed from what CNN blocks are to typical CNN architectures with blocks, and a small exercise for yourself to try and code a type of CNN block. So as we saw before, this is just a recap. CNN blocks, they're pre-designed reusable modules that consist of a combination of layers such as CNN layers, pooling layers, activations, batch normalization layers. They basically can be stacked together, right, to form a complete CNN architecture. Essentially, they're reusable components that repeat one or more times, typically in stages. That's what you'd see in the implementation of architectures like ResNet, ConvNext, MobileNet. They typically have stages where each stage has a certain number of blocks with a different configuration of, say, the input channel size, the output channel size, or the channel sizes of the intermediate layers, so on, right? Some common examples of layers in CNN blocks are given right there. You have residual blocks, ResNet basic blocks, ResNet bottleneck blocks. The basic blocks are typically used in smaller versions of ResNet. I think ResNet 1834. Bottleneck blocks are more used in, I think, ResNet 50 and larger sizes. We'll also talk about depthwise separable convolution blocks, what depthwise separable convolutions are, and some of the advantages of blocks are listed here, although you might have already heard of this. Essentially, repeatable blocks make CNN architectures and design more systematic, interpretable, save parameters, right? They can be reused. They're more modular because we want to be able to code them in a way where we understand what each stage represents, right? And here's an example of a simple CNN block, right? This block has a simple sequential of just a convolution, batch norm, and activation being a ReLU, and that's all a CNN block needs to be, right? A block just has to have some combination of these layers stacked together in some way, and then these blocks can be stacked to form deeper and deeper CNN architectures. So what are residual connections? And why did they come into place? So before ResNet, people typically thought that deeper networks were at least as good as shallow ones, right? But when they actually got to training them, they often realized and found that the training wasn't as stable, and they found the problem of vanishing gradients, right? So as you stack deeper and deeper layers, the gradients ended up vanishing, and one of the solutions to that was to introduce residual connections. That's where residual connections even came into play. And the idea is to basically add the original input X to the output f of X of a specific network. In most cases of the famous architecture ResNet, right, you want to do this across blocks again and again and again to be able to preserve these gradients through this residual shortcut connection or skip connection, right? These are the terms that are typically used to describe this. And it mitigates the problem of vanishing or exploiting gradients in deeper networks. It helps in faster convergence, right? And it also helps the model learn complex functions. And this is basically an example of a basic block on the left, and this is the bottleneck block. A basic block just has two 3x3 convolutions and a ReLU between them and a skip connection. And you can see here that the bottleneck block is a little more involved, where you have 2 pointwise or 1x1 filter convolutions. They're typically called pointwise convolutions, and you have a 3x3 in between. And as always, the skip connection from the beginning of the block to the end of the block. And here's how a simple basic block looks like, right? I've kind of shown you how exactly the structure looks here in the comments, but you have a convolution layer, a batch norm layer, a convolution layer, a batch norm layer. two 3x3 convolutions, and it's a repeat of just this structure, right? Conv batch norm value 2 times, and the residual connection from the start to the end. In case sometimes maybe you're trying to implement a custom architecture where the input channel size is not the same as the output channel size, or you may find in typical architectures as well, in standard architectures. But yeah, in case that's not the same, you also want to have something like you want to be able to equalize the dimensions, right? Because otherwise you can't add the input to the output if they're not the same dimensions. So you typically will have a convolution layer that makes sure that, you know, the size that's being propagated through here ends up being the same across the input and the output, right? So that's why you have this block of code which says if the stride is not equal to 1, which typically means you're going to reduce the dimensions of the image in some fashion, or the in channels is just not equal to the out channels, you want to have a convolution and a batch norm pair that makes sure that the input size ends up being the output size, right? So and therefore you can then end up adding it, right? Y plus equal to self-rut shortcut, that's the residual connection, that's what you're adding. And the bottleneck block here, the variant here, is just a more expanded version of the basic block where you have 2 point-wise convolutions, a 3x3 convolution in between, 1 point-wise or 1x1 convolution at the beginning, and another 1x1 convolution at the end. And it's a similar structure with the con batch norm value type archetype. And yeah, as you can see here, the channels right in between are reduced by a factor of 4 here. So you can do anything in between as long as you make sure that you're able to add the input to the output at the end, and you're able to make sure the dimensions match, right? This lets the network learn more complex functions, more complex feature spaces, right? Latent features, extract better latent features from the image and the like. So yeah, you have here 2 convolution batch norm, another con batch norm pair, another con batch norm pair, right? And then here in the forward, you go through this step first, right, in the first line, and then you go through the second step, then the third step, and then you make sure that you add the shortcut at the very end, and then followed by an activation there. So that's basically it. Depthwise and pointwise convolution blocks. Let's try to understand what a depthwise and pointwise convolution is. Depthwise separable convolutions basically split a standard convolution into depthwise and pointwise parts. Now, what is each part? Depthwise convolutions basically apply a single filter per input channel. So the number of parameters gets reduced by a ton, because in a standard convolution you have the number of, in a traditional convolution, the number of parameters is typically the number of channels times the number of filters times k cross k parameters, right? The filter size, where k is filter size. But in depthwise convolution, since you apply only a single filter per input channel, you end up having just channels times the filter size, right? And now that has a huge reduction in parameters where the number of filters is now eliminated from the equation. And what are pointwise convolutions? They're just basically reduce the filter size to 1x1 from a traditional convolution, right? And they're basically faster, obviously, because they're using a smaller filter size than standard convolutions. And combining these two gives you a more efficient parameter like configuration compared to standard convolutions. So for example, a 64 channel 256 filter 3x3 convolution, you end up getting 1.47 million parameters, right? Because you're multiplying 64, the number of channels times the number of filters, which is 256, times the filter size, which is 3x3. In the depthwise convolution, now we just have a single filter per input channel. So it ends up just being 64, right? 64 times 1. Then you have the filter size, which is 3x3, which is then just gives you 576 parameters. Now you've that's just like you remove 1474, you're left with just the 500 part. That's all you're left with, which is an insane reduction in parameters. And then with pointwise convolutions, you retain just the channels and the filter size, the number of filters. So it's 64 times 256, which gives you around 16,000 parameters. Now you combine both of these two and then you just get 9 times fewer parameters than the traditional convolution, right? So this reduces computations while maintaining accuracy in many cases. It isn't guaranteed or anything to be better or worse. You'll have to try it out and check which works for your specific use case typically. But these were used in quite a few famous models like exception, mobile nets, and connexts. So this is a typical depthwise separable con block. You would, in Torch, the way you would implement a depthwise convolution is you would use the groups parameter, right? The groups equals the number of channels. That just means that you have to use one filter for the channels, and pointwise convolutions just specify the kernel size as 1. That's basically it. So these are the two key changes that you would make to typical convolution layers to implement depthwise and pointwise convolutions. So the exercise, we're here at the exercise, the end of the recitation. What the goal for you to do is to be able to go and read the connex paper, which is linked here. And before I go to this stage, let me kind of explain how these papers usually work. They'll usually have a architecture diagram that explains how these blocks look. Like this is an ResNet paper, right? A residual block. And then they'll have some math that you can go through, and then you'll have typical comparisons with other architectures, right? And then this table typically describes what exactly the different variants of ResNet are organized to be. And this is what I meant by stages, right? Each specific entry in a single row is a stage. You have 3 such blocks with like this specific configuration, 4 more blocks with this configuration, 6 more blocks. This is the exact same type of block structure we saw for bottleneck blocks, right? It's a 1x1 convolution followed by 3x3 convolution followed by another 1x1 convolution. And it's the same here, right? You have another 1x1 convolution. So these are all bottleneck blocks with different configurations of in channels, out channels, and the middle channels. Here, they're just the basic blocks, right? Just 2 3x3 convolutions. But these are the stages that you have to understand how to build these networks. So once you implement a block, you can just maintain a stage configuration list with all this information, loop over it, and for each stage, you would just append or create these ResNet blocks, append them to a list, and then finally execute this entire list through an input in your forward function, making it really modular and a lot less elaborate and clunky, and makes it more interpretable, if you will. So similarly here in the connex paper, you also do have the diagram for a simple connex block. You see a connex block here. It seems to be a depthwise 7x7 convolution first, followed by a layer norm, a 1x1 pointwise convolution, and then which expands the number of channels to 384 from 96 by a factor of 4. And then you have another 1x1 convolutions, which brings back the channels or downsamples it back to 96, which is, also has a gallery in between. And this way you're able to start with a specific dimension and add it to the output without having to do any sort of, convolution to match the input and output size. So all all connex blocks start and end with the same function. Whereas the ResNet block, as you can see here, doesn't necessarily start and end with the same, right? It does, sorry, my bad. It starts with the 256, you downsample that to 64, right? And this downsampling portion, yes, is typically what we call a stem, right? In almost all networks, you have a specific stem, which is to basically reduce the dimensions of your input image, which might be really large, like maybe 1024 cross 1024, 512 cross 512. You want to reduce it so that you can extract useful features by downsampling them. And that way also make sure that you're able to have efficient computation, because if you retain the whole size throughout the computation, your number of parameters is going to explode, and it's going to be really hard to train networks too, right? So in downsampling, you're getting rid of the features that are probably things that don't really contribute that much to your task. Noise, right? Things that are in the background. Maybe if you just want to detect edges, you're only concerned about edge information, right? You don't really want all the information in the image. So downsampling it and making the network learn what features to spot with that reduced dimension size helps you make sure that the network focuses on a very specific portions of the image that is essential for your task. That's why you typically have the stem, and followed by the stem are typically stage configurations of the connex block that you implement. So this is how you would proceed from here to implementing networks for your homework 2, right? You implement a block, and then you look at these papers, you look at the stage configurations, and then you implement the entire network in a for loop in your init function. Right here is the exercise. We've given you quite a bit of hints as to how to implement this. You can always refer to the paper and then make sure that you complete this and verify this with with this specific block right here, the exercise block. Feel free to ask any questions. It's been a pleasure. I'm Vish. And yeah, thank you so much for this, for attending this recitation.